This is IAQ Radio, Indoor Air Quality Radio, the voice of the indoor air quality industry, with your hosts, Radio Joe Hughes and the Z-Man, Cliff Zlotnick. And now, Radio Joe Hughes.
Good day and welcome to IAQ Radio Plus. This week is episode number 508, and we taped the show live from the University of Texas, Austin, for the open house of the test house that is part of the Sloan Foundation Chemistry of the Indoor Environment program. Our guests are Dr. Richard Corsi, Dr. Atila Novoselic, Dr. Marina Vance, and Dr. Delphine Farmer. I also want to thank Bob Krell of Healthy Indoors Magazine for helping us do this show. We also have included some extra interviews that Bob did with a few of our guests and a walkthrough of the test house. So hope you enjoy the show. Let's start by introducing the guests for today's show. The first one is Dr. Richard Corsi, who is the Joe J. King Chair in Engineering in the Department of Civil, Architectural, and Environmental Engineering at the University of Texas at Austin. He served on the faculty at UT Austin for nearly 25 years after starting his career in the School of Engineering at the University of Guelph in Ontario, Canada. He is a highly regarded educator and has received numerous teaching awards. Next is Dr. Delphine Farmer. Dr. Farmer is an associate professor in the Department of Chemistry at Colorado State University. Her research focuses on building new instrumentation to measure reactive trace gases and particles in the atmosphere in order to understand how humans are changing our environment. She is particularly interested in emissions from forests and has recently taken the dive into the complex world of indoor chemistry. Our next guest is Dr. Attila Novoselic. Dr. Novoselic is a professor at the Department of Civil, Architectural, and Environmental Engineering at the University of Texas, Austin. He has BS and MS degrees in mechanical engineering from Belgrade University and a PhD in architectural engineering from Pennsylvania State University. The goal of his research is to improve buildings with respect to their impact on occupants and health and energy performance. He conducts both fundamental and applied research that leads to healthy and efficient buildings. And we also have Dr. Marina Vance. Dr. Vance is an assistant professor in the Department of Mechanical Engineering with a courtesy appointment in the Environmental Engineering program at the University of Colorado Boulder. Her research is focused on applying engineering tools to better understand and minimize human exposure to novel environmental contaminants from everyday activities and the use of consumer products. Her group focuses on the physical and chemical characterization of ultrafine aerosols or nanoparticles in the air. So HOMEChem stands for House Observations of Microbial and Environmental Chemistry. And we started the interview by asking Dr. Novoselic to describe the house, the age of the house, and what type of house it is. So we're going to turn it over from here to the interview that was live at the University of Texas, Austin.
Pretty much the house is built in 2007, and since then it has been used for various experiments, specifically for indoor air quality and building performance. And yes, it is pre-manufactured at home, typical for practically, I think, significant fraction of population. So it is retrofitted quite a lot for running experiments specifically associated with air quality, and the house itself is not as valuable as what is happening in the house, and if you just look, every single instrument here is probably more valuable than a house, but it's really give us a great opportunity to run these full-scale experiments.
Is there $5 million worth of equipment here somewhere? Is that what I heard?
We counted $4.5 million.
$4.5 million. Okay, that's Dr.
It could be a
Vance.
little more.
And it's just fascinating, all the equipment throughout the room and throughout these buildings. But the questions you're trying to answer are, what are the sources of chemical oxidants in the indoor environment? How are they impacted by changes in light conditions and human activities? The second one is, what are the main sources of organic compounds in the indoor environment? And there's more to that, but we'll get back to that in a moment. And what are the sources of indoor reactive nitrogen species, and to what extent is their presence indoors influenced by outdoor air pollution? That's a mouthful. Tell us a little bit Dr. Farmer, you're more of an outdoor person, right? The chemistry outdoor person. What's your role here with the project?
Yeah, so my history has been really in thinking about outdoor chemistry and how things like forests and humans can influence the air we breathe outside. So I was brought on and met Marina Vance, and we started thinking about what's happening inside, and it is absolutely mind-blowing. There are so many more molecules inside than we have seen anywhere outside. And I've been doing urban air quality studies in places like Mexico City and all over the United States. And indoors inside a standard little house here in Austin, Texas, where the outdoor air pollution is really not that bad. It's pretty clean here. Indoors, it's just a whole different ballgame.
And Dr. Vance, I believe you worked maybe a little in the indoor air world prior, because I know you, Dr. Hernandez, we've been on the show, Mark Hernandez. And what's your role here?
So I don't come from the outdoor atmospheric chemistry world. I'm an environmental engineer, and my background is on assessing people's exposures to real-world situations involving consumer products and other, real-world scenarios. So coming to HOMEChem and thinking about the experimental design and how we could make HOMEChem assess real-world situations was sort of my job in the campaign. So I come very much from an indoor world experience. I've assessed the release of nanoparticles from the use of consumer products and air pollution or aerosols emitted from things like 3D printers and other office products.
Okay, let's start with the building itself. Let's go back to Dr. Novoselic. The building we talked about is manufactured housing, 3-bedroom?
Yeah, 3-bedroom, 2-bath, so 1,200 square feet.
And you have 2 mechanical systems, one in the actually 3, one in the crawl space, one in the attic.
Yes, pretty much when we bought this house, we wanted, it was designed practically with the idea to run different experiments, and in some situation we wanted to have underfloor supply systems, in other overhead, and those are 2 typical air systems, air distribution systems, which are probably 90%, 95% of US homes. However, we have also project, in one of the previous projects, we looked how the hydronic system operates in the house, and we built the 3rd one. Pretty much that's a thin coil based with chilled water and hot water distribution systems. So again, depends on the experiments. We turn on one or the other. In this one specifically, we use the air overhead system, which is the most common.
That's why I noticed the floor registers are taped off right now. You're doing most of the air overhead because it's the most common.
It's most common, and it was most suitable for this experiment because we wanted to have as good as possible mixing in indoor environment so that we don't get position-sensitive measurements. So we operate this house as pretty much single zone so that our results are not spatial dependent. And this way we focus on phenomena which we want to isolate, not so much what will be the air distribution and how will it move from one room to the other.
Okay, and then I also, you're doing tracer gas testing, or you were at one point. Who's doing that, and why were we doing it that way as opposed to, I don't know, did you do blower door testing to get the tightness of the home?
Yes, there was probably 2 months of preparation for this experiment by what we call building characterization, and among many other stuff we did a blower door test, which is a standard test for measuring air tightness on envelope. And this one here at 50 Pascal, we have something like 6 to 7 air exchange rate, which is relatively airtight home. So pretty much it's not zero energy home, but it is better than typical home. Which,
tighter than
typical home. So, but very close practically, or let's say, yeah, very, very similar to most homes.
I'm curious about the crawl space because we have a lot of problems with crawl spaces. Is it is it a conditioned crawl space?
No, it is not. So this is it is vented crawl space. So the air is well circulated because that was one of our previous measurements. We used tracer gas to see what's the air exchange rate in the crawl space, and also we did, as a building characterization, we measured what's the communication in between crawl space and occupied space. So, but there's a test which we developed, and it came out that it's very airtight, so pretty much it is hardly measurable. So if the fresh air comes into this house, it comes through the windows, small holes for penetration, but for this campaign specifically, we are running dedicated fresh air supply system. So we have a supply air which is constantly pumping air, outer air into the space, because we didn't want to have fluid dynamics affecting measurements. So, and we didn't want to be weather condition dependent results because we have variation in the weather conditions. And since this is experiments we repeat some experiments with some perturbation. Probably Nina and Delphine can talk more about that. Should probably in a minute. But the idea was really to exclude ventilation as a variable in this experiment.
I said you want to exclude ventilation altogether.
No, impact of no. We have ventilation, but variation in ventilation.
Okay, variation. You wanted to keep it consistent.
Exactly.
When you check the crawl space system, how much of the crawl space air got into the house?
Actually, almost nothing, because we managed to have a slight pressurization of the house with a fresh air supply, and pretty much we don't have almost these experiments are we don't have. Of course, the beauty of a test house, in one of the experiments actually punched the holes in order to produce that, but not in this.
Okay. But what about the attic? You've got a system in the attic. Is that a conditioned attic, or is it also ventilated?
No, it is a tight attic, just naturally ventilated. It's a very small attic because it's pre-manufactured homes. They don't have tall attics. This is just probably 8-inch thick crawl space, and it's vented by outer air. But again, the pre-manufactured homes are well built. I'm not sure that they use the best materials, but this one here is very airtight, and it's still airtight, and we don't have all the communication with attic.
Another question came to my mind when we were talking about the, on your mechanical system, what type of filtration do you have?
So for this specific campaign, again, we decided not to focus on filtration systems. So we have, for fresh air, we have very coarse filter just to prevent that bugs get in. And we practically mimic infiltration, because infiltration is coming through cracks and windows under the door, and some particles get stopped, large particles. That's what we do in this with our mechanical ventilation system. But we don't filter ozone, we don't filter pretty much anything which is happening into the in-house, because we are focusing here identifying chemistry, and we didn't want to take away that.
Sure, and you want it to be like a normal home. I mean,
yes, so practically, yes, exactly.
So let's start with Dr. Vance for just a moment. Can you tell listeners a little bit about the different types of experiments that are going on here? And are you the best, maybe Dr. Farmer? Yeah. Okay.
Yeah, absolutely.
Is it like 20 different?
We have different categories of experiments, and we have different activities performed for each experiment. So first we have the types of activities that we have are based on everyday activities that people would be performing in their own homes. So we're focusing on cooking, cleaning, and the use of personal care products or occupancy. So for cooking, we have chosen a few experimental meals. We have a breakfast meal, we have a stir-fry meal for lunch, and we have a chili meal for dinner. We also tried a lasagna. We have different experimental meals. All of them were decided on a basis of chemistry and whether that's a common meal that somebody else might be making, at least in the United States or in the Western world.
The students do the cooking, is that?
So we have anonymous volunteers performing the activities in the house.
I see.
Yes.
Okay.
So that's cooking. For cleaning, we chose mopping the floors as our experimental activity because it's very easy for us to get a mass transfer from the water phase, the things that you put on the floor, to the gas phase, and then we can watch that chemistry happen. We have 3 different types of cleaning products that we're testing during this month of experiments. We have a pinene-based cleaner, a chlorine-based cleaner, and then an all-natural, advertises all-natural cleaner as well. We might actually add a different one for the last week as well. We're discussing some, as we watch the data real time, we make a few changes to the experimental design. And the last category is the use of consumer products and human occupancy. So for that experiment, we don't have any activities performed in the house. People are simply invited to come in, occupy the space. They're usually working on their computers. But then we have a little bit of input on the types of personal care products that they use before coming in that day. So we had 3 different days of activity. The first day was the use of all natural products. So things that are advertised or according to your own perception, what do you consider to be cleaner, greener, more natural? And that's what people were, advised to wear after their last shower.
What's an example of something people think is cleaner and greener?
There's brands of deodorant that say, they're aluminum free, so they're all natural. And there's organic brands of shampoo and hair conditioner, that say that they don't use phthalates and they don't use other organic compounds, and it's just going to be very interesting for us. My personal hypothesis was, is the VOC emission any different from a regular consumer product? So that's day 1 of experiments. Day 2, people are the same people, roughly the same people come in, wearing what they usually wear on an everyday basis. Most of the volunteers are from the academic world. I think their average use might be low compared to some other cultures. I'm not sure. We'll find out. And for the third category is the go crazy on your products day. Pretend you're going to a really important party and you really want to put on a lot of, perfume or other categories of products that you may consider that are strongly scented, and we'll see if we can tell a difference, not just in concentration, but in the types of chemical species we can detect in the air.
I know you're not done, right? We're still doing this. Is there another week of...
There's a whole other week left of HOMEChem, yes.
Okay. Are there any early little pieces of info you can give us, some of them maybe off these posters? Or?
Oh, sure. What we found is, it's been so interesting, as Delphine already mentioned a little bit, the concentrations of volatile and semi-volatile species and particles indoors are much, much higher than outdoors. Most things are much higher than outdoors. Something like ozone is a lot lower indoors than outdoors. In fact, we've had very little ozone detected in the house. And in terms of particles, what's already been shown in the literature is that whenever you have a cooking event, you have a huge, huge spike of particulate matter happening indoors. And that's something that we've confirmed over and over with very good repeatability during HOMEChem. So,
just particulate, or do you also see spikes in
volatile organic compounds? Very much so, yes.
Very big. Okay.
Yes.
And, we've heard 3 to 5 times higher indoors than outdoors, or 3 to 10 times. Are you seeing even more?
Probably more. It depends on the species, but yes.
Well, let's ask Dr. Farmer. What are you seeing? This has got to be all kind of different for you.
Yeah, we are seeing everything. And I'm not actually joking about that. We have these instruments that are incredibly sensitive. So, for example, my group has been building mass spectrometers where we can detect all sorts of unique molecules. There are research groups here that have brought these fancy gas chromatograph instruments. Every instrument is seeing peaks of molecules across every sort of gradient we can imagine. So across every type of volatility, every type of carbon, every type of nitrogen species, we're seeing huge numbers of them and a very large diversity of molecules. And I think it's the diversity that is astounding to me, almost even more than the concentrations themselves. The concentrations are high, but it's not just 1 or 2 things. It's everything in the organic carbon sort of realm.
You did mention ozone was lower.
Yeah.
Were there any other
Yeah, so sulfate aerosol, which is one component that is, you release sulfur from, say, diesel trucks, and that gets oxidized and forms sulfate aerosol particles outside. Coal-fired power plants are another source of that. We see that outside. We see much less inside, though we still see some. So that's another example of a molecule we're seeing outdoors, but not indoors.
Now, the experimentation is when you're doing the occupant simulations. Those are for short duration, right? You have the volunteers coming in for a short period of time, so you're not getting 24/7 occupancy.
Well,
so how do you account for that?
So we're not getting 24/7 occupancy. We're getting things. So, for example, the mopping, the volunteers will come in and mop for about 10 minutes, and then they leave. And the cooking can take a little longer, and then the volunteers are, of course, encouraged. They get to sit down and eat the meal that they just cooked, and then they leave. So most of those days, the occupancy is in little bursts of maybe 20 minutes up to about an hour. On the other type of day that Dr. Vance just talked about was the layered days, where we have people coming in the morning and they cook breakfast, and then they clean, and then they cook lunch, and then they clean up, and then they cook dinner. There we're talking occupancy from around 8 in the morning through till about 6 o'clock in the evening. So we're getting a much larger array there. And then in the evenings, we don't have any occupants, and we allow the house to sort of resettle back to just a house background itself. And so we watch, and for some molecules that just takes a few minutes to re-equilibrate, for the walls to then find their equilibrium with the air again. Other molecules or particles, it might take several hours to do that. And then the next day we're restarting.
Okay, I'm wondering, maybe this is for Dr. Novoselic, did you repaint before this all started, or is this 11-year-old paint?
Most of the house has 11-year-old paint. However, you will see some imperfections in the paints, and because again, the house has been used for many years, and sometimes small experiments really included hanging out some gigantic panels of passive removal paint. So panels with passive removal paints, and that was removed a long time ago, but there were some stains, and we just fixed. But yes, this is most of the house. 90% of the surfaces is the original.
Formaldehyde. We hear a lot about formaldehyde in indoor environments. Who would be best to talk about what you're finding? Are you looking for? I'm sure you're looking at formaldehyde. What are we finding?
Yeah, so formaldehyde is a really interesting molecule. It's really small, and it's incredibly challenging to measure. So we do have one instrument that is capable of making a very accurate measurement of formaldehyde, the UC Berkeley's proton transfer reaction mass spectrometer. Bit of a mouthful, but a really cool instrument. And that one is capable of measuring formaldehyde. What's interesting to me is that we talk to people, and formaldehyde is at the forefront of everyone's mind in the indoor air quality world. But it's just one small peak in our instrument, and there are lots of other molecules out there. So we're certainly seeing it, and it's there, but relative to everything else in the home, it's actually quite small. So when it comes to thinking about long-term effects, that's a different question, and I don't have an answer for you yet, but we'll be investigating those sorts of questions over the next year or two.
So one question I had is, I know you're looking at ultrafine particles. That's part of your study. Any revelations there? I mean, I think that's in the indoor air quality industry. It seems to be a constituent that people don't look at enough, at least as far as the practitioners in the field. Certainly on the research side, I think you do, but in the field, there's limited instrumentation to go out and do real-time ultrafine particles.
I agree with you, and there are multiple reasons for that, right? There's limited instrumentation, and then all of the regulatory standards. I know there are no standards for a home environment indoors, but we base all of our decisions on the regulations that we see for outdoors, and all of that is done on a mass basis, right? But then if you look at ultrafine aerosols and their potential health effects, they amount to almost and what we're seeing is that there is a huge amount of ultrafine aerosols, especially during cooking events. Particles grow over time and they become bigger and bigger, but really the peak, if you look at the number of particles present indoors, their peak is definitely in the ultrafine range, so less than 100 nanometers in size.
And you're seeing that more during the cooking phase? Is that, I know Lawrence Berkeley Labs, did that research several years back and saw a lot of spikes during the time when they were actually cooking.
Yeah, exactly. And we have a gas stove in the test house. It's running on propane. The second you turn on the gas stove, you can already see some particles, and then the moment you start cooking, then as you can imagine, you can see things coming off of the food. You're heating up your food, and what's happening is a lot of the organic material that's part of the food itself, and the oils and everything else, is evaporating in the high temperature of the stove, but then they encounter room temperature, which is much, much lower, just a short distance away, then they recondense back, and then the form of very, very small particles.
So we're here today at the UTest house, and this is part of the HOMEChem project. So this is a month-long project you're running?
Yeah,
right?
yes, yeah.
So you're at the end of it, correct?
We still have 1 week left to go.
Okay. So a lot of good stuff's happening, but you still have a bit more to do here. So obviously, what's the end game for this? What is your intent? What do you expect to glean from this project? Overall, what's your looking at it 10,000 feet?
So from a 10,000 feet standpoint, we want to get better insight on the chemical reactions that are taking place indoors and other chemistry-based processes. There's been decades of research on trying to understand the indoor air quality, so focused on specific compounds and particulate matter and, some indicators that we can monitor to get an idea of the quality of the health of the environment and, get an idea of what the health outcomes might be from those. But there is very little information on the chemistry that's driving those emissions, and then other compounds that are not part of that select list that's been monitored over decades. So we're trying to start getting an idea of those chemical processes. Do you want to add anything, Delphine?
Yeah, I'd say the other part of what we're really trying to do from a 10,000-foot view is to understand how to study indoor chemistry, right? How do we build an experiment? What instruments can we use inside? We have all these instruments that we normally use outside, but the concentrations are much lower. The types of molecules are very different. So do those instruments work well inside? And how do we design an experiment to study indoor chemistry? So we're really hoping that this project gives us the insight to move forward in the future in the field.
So the thought is that this actually is almost a pilot in that regard, to the extent that you're actually trying to prototype how you would actually do a more advanced study or a more detailed study?
Yeah, absolutely. I mean, there's thinking about it as a pilot project or a big first step. This is not a small project, but it is. We're as we move forward for the month, we've been learning more and more about how to do the experiments and how to make the measurements. So it's a learning process as well.
And also, when you think about the scientific process, right, when you think about the field of indoor chemistry, we can't answer all the questions in a month. Even though this is a month-long experiment with over 60 researchers, over 30 pieces of instruments, we can't answer all of the questions. What we're going to end up doing here is raise more questions and bring them out to the field and point them to other researchers and say, look, we've identified these things, now can you help us? And hopefully that's going to help drive more research into looking into indoors, into the indoor chemistry. So we're inside the UTest house. It's in Austin, Texas, at the University of Texas at Austin. It has 1,200 square feet of area, 3 bedrooms, 2 bathrooms, a little shared kitchen and living space. And we have placed a lot of our instruments in the middle of the house. So the kitchen is over here on our side, and then right on the hand side, you can see a suite of particle size instruments. So if you think about particles in air, they can range in size from all the way to very, very small clusters that only have a few atoms and can be 1 nanometer in size, all the way up to what we call almost like boulders in the air that can go up to 20 microns that are picked up when you walk and move. So the suite of instruments is looking at all of those sizes. So the first instrument here is looking at particles from 1 to 4 nanometers nanometers in size, so the smallest particles that you can imagine. Anything smaller than that is not a particle. It's going to be in the gas phase. And then this instrument is looking at the next size up from 4 nanometers to 120. And then their inlets are all located here near the stove. And then if we follow that inlet to the next instrument over there, it covers the next size up. So that one is going from about 100 nanometers to 600 nanometers. And then all the way from 500 nanometers to 20,000 nanometers, or 20 microns in size, which is the largest a particle can be in the air. Otherwise, it would just fall back down to the ground. That's covered by this instrument.
So the thoughts with the ultrafine particles are definitely something that you're considering.
Yes, definitely. So we are looking at the ultrafine particles using 2 different instruments, and then the smallest ultrafine particles possible with a third. So we have real-time measurements at all times, 24/7 throughout the house. So as activities happen, we can link back the specific activity to the particles that were emitted.
We'll take you over to see an array of the sensors that we have here in the house. So we've got sensors that have come from an array of different companies, but we also have some that are home built from different universities. So we have Harvard sensors, we have Washington University and St. Louis sensors, and then we've got some other slightly higher end sensors from some sort of intermediate cost sensors, the portable optical particle sizers, which are in here. These come from Handix, and then we have the University of Colorado at Boulder also has some home built sensors. So we're putting all of these here and in a couple of other places around the house so that we can compare them to the really high-end measurements that we have. So this gives us 2 pieces of information. It tells us how well the sensors work, and then it also tells us a little bit about spatial variability. When we take these sort of intermediate cost sensors and we put them in different rooms of the house, we can see how different rooms of the house respond to different events like cooking. We have a lot of supporting stuff here supporting measurements here in the test house. So on the ceiling you see taped to the walls all these different little gray wires. What they do is hold thermocouples, which measure the temperature on the walls, and then we have thermocouples and other measurements all the way throughout the house that give us temperature readings, and that's going to help us be able to model the data and interpret the results. We also have these little white blocks that are on every door, and these are part of a smart sensor system that tells us every time a window is opened, every time a door is opened, every time a fan is turned on or a light is turned on, or the oven is open when we're cooking, then we can help use that to really interpret the data. What you can see here in these 2 large boxes are actually little laser cells, and so the group from Indiana University is measuring OH and HO2 radicals as well as nitrous acid. And so the question is there oxidative chemistry changing what we're breathing inside the house? Those are really hard measurements to make, so what the Indiana group does is they've got a laser inside one of the trailers outside, and then they just send that light through a little fiber optic cable into these large boxes, and then they bounce the light in between these little sample cells that are buried in here, and then they can tell us what exactly the OH and HO2 and HONO levels are. So these are really reactive compounds. They're right next to the window because we think this is the best chance of actually seeing that kind of chemistry because they require a little bit of light.
So this is the 3rd bedroom of the house, aka our control room. So we have this big panel that was set up by Attila Novoselac and his group at UT Austin. So here they monitor all of the building parameters of the house. They understand the ventilation rate really, really well, and they have all of those temperature sensors throughout all of the surfaces of the house and CO2 measurements as well, and all of that data is collected here. So this is definitely not your average house.
Chairs on the break, and we brought in Dr. Richard Corsi. Welcome back. It's been too long. It's just good to have you. This is a great event. I'm sure you're up to your ears with things to do, but if you could just, what's been your biggest, what's your biggest take home for the listeners? You know, you do in the field kind of thing. What would people doing IAQ investigations, what are they going to learn from this?
So, great question. I think that we've been doing research on indoor chemistry decades now. Without the tools that are being brought to bear here in the HOMEChem study, we've noticed a lot of things in indoor environments, but never really fully understood them. And I think this study is going to help us to better understand things that we've observed in the past, but never really understood why they were happening. We have a lot more sophisticated instrumentation, measuring a lot more things measured simultaneously before. And I think between the cooking events, which are telling us a lot about how cooking, especially cooking with gas, affects indoor chemistry, and the cleaning events, which tell us about different types of cleaners and how they affect indoor chemistry, we've never really dug into those things to the depth we've needed to in the past or could in the past. And those are two activities that are very, very common activities that were built into the program by Delphine and Nina when they were planning this program that I think are going to tell us a lot about those kind of extreme events, those extreme conditions that happen in people's homes that generate bursts of chemistry in the house.
We've been tied up, haven't got a chance to look around. What kind of ventilation do you have over the, is there a hood over the stove, or what do we got going over there?
So there is a hood over the stove, but in order to keep this experiment as representative to the average home as possible, we're not using a hood over the stove. We are not. From anecdotal evidence and just talking to everyone I've noticed several people don't actually run their hoods or don't have a hood, and we wanted the study to be more general about the emissions from cooking. And then, and I know there's been some studies, including the Lawrence Berkeley lab, on individual hoods. So we didn't want the specific model and flow rate of this specific hood and the type of filtration system that it has to dictate our results.
Just to add something that Nina said. So in one of the cooking events, at least looking at some of the preliminary data, the data suggests that people need to use their hoods.
Yes.
Right? So we have extremely high oxides of nitrogen concentrations, which, especially nitrogen dioxide, can be quite harmful to the occupants of buildings. And
respiratory or?
Yeah, it's a respiratory aerosol for sure. Yeah. So I hope that by doing this kinds of research and looking at things at the level that all the researchers here are able to look at, that perhaps it'll lead to changes in building codes. Perhaps there shouldn't be homes built anymore in the United States that don't properly exhaust, stoves and ovens, right? And and ought to be even in home sales. Perhaps if you don't have an exhaust vent, you should be required to retrofit so you can exhaust the outdoor, which my wife and I had to do in our home. We had one of those stove hoods that just basically circulated the air right back in our face going through a grease trap. So I think the results from this study are already telling us something, the preliminary results, about the importance of ventilating while you're cooking.
Okay, go ahead.
And I just want to add one anecdote to that effect. The Drexel University folks have brought a very sensitive aerosol mass spectrometer that looks at particles. And they actually brought it with the same group of people that they sent out to Kathmandu in Nepal. And they were looking at emissions in outdoor systems, air in Kathmandu, with these massive amounts of really dirty cooking, right? So freestyle fires and then solid fuel. And so there's a huge pollution problem in Kathmandu. And the levels that they're seeing inside the house when we say cook up Thanksgiving turkey are substantially higher than anything they saw in the air in Nepal when they were there. So that to me really just reinforces the idea that ventilation and really thinking about this indoor source is incredibly important.
All right, let's go over to Corbett Lunsford. I just wanted to introduce Corbett. Corbett, I know you've got a tiny house and you run around the country. You're a TV star or will be. Is it on yet?
It's not on yet. It's called Home Diagnosis. We're proud. It's the first TV series ever about building science and about home performance, which this is an important part of. Somebody like me, Grace and I are both on this project as not researchers. We don't really belong in this lineup. We're more implementers and communicators. And so what's really shocking to me is that the amount of information that is gotten by the academic community about buildings and about indoor chemistry and atmospheric control, all this stuff that is very, very applicable to what I do as a contractor and as anybody in the building industry would say, it does not get shared down the ladder. And this is less on the technical side. But I think that what we've been learning is that there are things that we can incorporate from the academic research, and the amount of diagnostics that somebody like Attila is doing on this house, like he's been testing this out for 11 years. I spent 5 hours in somebody's house.
Right.
So, one of the things I want to do while I'm here is sit down with him, taking lunch, and be like, what else can I be doing with my 5 hours that's going to be anything close to what you're finding out? But I think that all of the proof, and the proof is possible message is really what we're trying to focus on. It's not about energy efficiency, it's not about comfort even, it's about like control. Do you want to know for a fact what's going on in the house? And that is so critical, and this is where we find out what is actually going on. And this is like the beginning, right? The tip of the iceberg is this month. And I think Richard said that we're going to find out more in this month of testing than we have in the last 2 decades of testing, because the instruments that we're using are so much better. So when we're spending this amount of money and time, and over the next 10 years, what we find out is just going to, I hope, revolutionize the entire construction industry. Do you have anything you would add?
Sure. Hi.
Hi.
Thanks for welcoming to the party.
Grace.
Well, I think for me, I think the unique part of being on this is I am like the general American public who maybe has a little bit more of an intrigue because I've been married to this guy and telling his story for a couple of years, and so I understand it. But at the same time, I've just had 2 babies in the last 2 years, and which still sounds kind of incredible. But a lot of this indoor air quality is very concerning to me, and they're tiny little systems, and the cleaners I use, and frankly even how I cook. That's now something that I'm reconsidering. We're about to build another house, and we've got to decide on the kitchen. Do we go gas? Do we go electric?
We're just going to boil everything, I think.
Yeah. Yeah.
I saw a video you did, I don't know, Corbin, you were on at the end, and you were like, I thought I knew a little bit about indoor air quality. I know nothing about indoor air quality, but I watched, there are a lot of energy, home performance guys getting into the indoor air quality world. What will you say to them now that you've had this experience here? I mean, are there tips you would give them? Is there some, I know I didn't give you this in advance.
No, that's great. I'm going to provide it. So,
what are your thoughts?
I mean, I would say the first thing is that everybody who's doing any work in homes is already working in air quality, whether they know it or not, right? And they're mostly doing things that are accidental, so they're going to be having effects on people's homes. When they put in a recirculating when they don't put in any back exhaust fans, when they cook all day long with the windows closed, anything like that, even homeowners are doing this. And
they have a downdraft vent, and they think it's working.
Right, and I think that the main problem that we have, and I'm sure that you already have seen this many times, is that we tend to open our mouth and we don't know what we're talking about. And I'd say that is how diagnostics can change the structure. So anybody can go in their house and run their mouth about what they think should happen. But really, once we have measurements, which I do on a very light level, and even as a guy who wrote a book about how to do diagnostics, what I do is nothing compared to what they're doing. I think the idea of measuring itself, if we can just get people to understand that you should measure things in your house and not just the size of your rooms for your carpeting, that is going to revolutionize the entire field. And hopefully energy raters will understand more about the indoor air quality side of things and understand that, I think what we're going to find out, and Sloan does not fund human health research, but once other foundations jump on board, what we will probably find out is what they found out elsewhere in the world, is that the health effects of home performance far outshadow anything that has to do with energy efficiency. Energy efficiency is nothing compared to the health effects.
I'm curious about carbon monoxide. Who can tell me about what you're doing with respect to carbon monoxide?
So one of the instruments that we have here on site is actually an instrument owned by Drexel University again. That instrument is measuring carbon monoxide, carbon dioxide, and methane really, really well. So again, we're definitely seeing it. We see it increase when there are cooking events, not too surprising. I will say that actually a little more interesting to me as a chemist is carbon dioxide, the CO2 measurements. And we see that, of course, when people walk into the rooms. We see these huge increases in CO2.
But when people were touring the house, you noticed that the carbon dioxide levels hit about 7,000 or 8,000 parts per million just with 15 bodies in here looking at the house, right? So that was, the equivalent of a party. People having a bunch of people over to their house for a party with the door and windows closed. And you superimpose on that, because you can superimpose the sources of CO2, superimpose on that the 7,000 ppm from cooking.
Yep.
So suddenly you're up to 15,000 ppm. If you're having a party with the doors and windows closed and somebody's cooking during the party to get the food ready for everybody, those are pretty high levels of carbon dioxide. We're getting to levels that would be scrubbed on submarines, right?
So you don't have to drink.
That's right.
Well, I think one of the questions too is like, the Harvard, Syracuse University, Syracuse Center of Excellence study, cited fairly low levels of carbon dioxide, basically having cognitive impairment. So what is, what's the difference between what's safe, or what's a true, clinical problem, or something that maybe at least moderately adversely affects the occupants?
So there's been 4 or 5 studies now by different groups on the cognitive effects of carbon dioxide, and they by and large conflict with one another. So there are teams in the Danish Technical University or in Scandinavia who suggest, or the research shows, that you get to pretty high levels without any cognitive effects. So I think this is still an area that needs more research. And the question really is, if the carbon dioxide is causing impacts, or is it something else that the carbon dioxide is an indicator of? You get a lot of people in a space, and carbon dioxide concentrations increase, but there's a lot of other things that people emit that also increase in that space. Studies like this are going to show what those things are. And it may not be the carbon dioxide itself, it might be something else associated with humans in the space that we're emitting, right? So I think the jury's still out on whether carbon dioxide itself is causing cognitive effects, or whether it's something else associated with the sources that emit the carbon dioxide.
And perhaps that's a surrogate, the carbon dioxide levels indicate what other constituents might be elevating.
So one of the studies just injected carbon dioxide from a cylinder into a space where people were and didn't see cognitive effects. And that was an indicator that perhaps it's not the CO2, it's something else associated with the release of CO2 that's also being released.
Okay, I've got another question here, and that is, there's some new types of testing and analysis. Is that accurate to say? Are you working on new techniques, or?
So we have a lot of new instruments and new technology here for all of the chemical measurements. So we have some new instruments that are commercially available, but as a university-based instrumentalist, I'm even more excited about some of the really cutting-edge technology that universities have been developing over the last couple of years. So we have instruments here where it's the first time they've ever been used to make measurements, and they are getting some of our most fascinating data. So one example is from the University of Colorado at Boulder. They have this instrument called an EC-TOF, which is a very long acronym that I won't even begin to attempt. What I will say is that it is not very easy to run. It's a very large mass spectrometer that is looking at specific molecules that are in particles. And so, for example, they can even see during Thanksgiving the molecules of certain oils from the turkey that are showing up in the particles in the air. So we have some of this incredible instrumentation so we can track and the organic molecules as they move through the house, and that we can actually start to think about where they're coming from. And just as Rich highlighted, I think this is one of the really exciting parts, is saying not just what are the carbon monoxide or carbon dioxide or formaldehyde, not just where is that coming from and what is it doing, but what about all the other molecules that come along for the ride that are present in really trace quantities. And so I think that's exactly what Rich was getting at, was this idea that there are all these other things out there that we're breathing. And so are those other molecules just being tracers for sort of the really interesting stuff here?
What about there's someone working on low-cost sensors and how accurate they are? Who can talk to me about that? Dr. Vance, you project well. Go for it.
So Dr. Corsi and I are collaborating on evaluating a number of low-cost sensors. Some of them have been supplied by the manufacturers themselves. We have scattered them throughout the house, and some of them we purchased them on Amazon. And what we figured was that this would be a wonderful opportunity to compare them against these high-end instruments that we have monitoring the house at all times. So some of these low-cost sensors are in the kitchen environment in the house, and some of them are in the living room. As Dr. Novoselic mentioned, the house is considered well mixed, but a lot of these particles can absorb onto surfaces and get lost, and some things can react away, as the air is moving through. So we want to get an idea of the spatial homogeneity in terms of chemistry and particles as well. So some of these monitors might actually help us. And we're also we're using the experiment to have the monitors help us, but we're also testing the monitors themselves and seeing how they fare in comparison with the high-end instrumentation.
I'm here with Dr. Rich Corsi. We're at the UTest house in Austin, Texas, for the open house at the HOMEChem project.
Yep.
So, how did today go for you?
I thought today was fabulous. We had great foot traffic through the test house, great questions, lots of ideas that people provided us on things that they'd like to see in future studies. So it was a really, really fantastic day.
So the intent of this project, this is a fairly short project. I would almost consider like a pilot study. I mean, in effect, because it's kind of a study about how to do a study. Is that?
Yeah, no, I think it's a real study. I think it's a study that's somewhere between what we'd say a large laboratory chamber study and a real home study. So the home that we're in right now is not an occupied home. It doesn't have all the things you'd find in an occupied home, but it is much more like a home than a stainless steel chamber, right? So it's a 1-month study. It's a very intensive study. There are more measurements being made with more sophisticated instruments in this study than have ever been made in any house, as far as I know, in the history of indoor air quality research. So I think it's more than a pilot study, but I do think a lot of information will come out of this study that will help guide future research. I think that we're going to see interesting things in this study that go deeper than anything we've ever seen before doing indoor chemistry research, and that'll beg the question of why certain things are happening and how would changing building factors affect those things that we see during this study. So we may want to come back, a year or 2 or 3 from now and investigate some of the things we see in this study in more detail and turn some of the knobs, try to figure out how changing the operation of the mechanical system or putting furniture in the house or those types of things will actually affect the results.
So you're very... you're satisfied with what you were able to achieve in this short window. I know you had a ton of researchers here. I mean, this has been like a 60-person team almost?
Yeah, there's 13 different universities participating in some way or another in this project. Some are not physically here, but they just sent their equipment down. Some of them have actually developed their own equipment and sent it down to UT for us to use. But I think there's about 8 to 10 universities that are physically here. The best and the brightest researchers in North America who do work on atmospheric chemistry, either outdoor or indoor. It's great to see the outdoor atmospheric chemistry crowd coming indoors because traditionally they've had a lot more research funding than we've had in those of us that do indoor chemistry research. And so they have much better tools, much more sophisticated instruments that we've never been able to really apply in the indoor environment again. And that's really what this study how this study is different, and it's going to bring to bear a lot of amazing data. It's mountains of data we'll probably be mining for the next many years. So
what's great about that, and I think I raised this during the IAQ radio show, and I applaud this research and what you guys are doing. Some of that information will get to the industry, as well as the practitioners. Some will.
Yeah.
The forward-thinking ones will.
Yeah.
We'll dig and find them. I think some of the industry won't get it, but how does it get distilled, and how does it get out to the general consumer in an actionable level?
Yeah, I think that's a great question. So, my goal at the end of all of this is to come up with a list of perhaps the top 6 or the top 10 things we learned from this intensive study that practitioners should know, and to boil it down in a very straightforward way. And I think we ought to be doing that more with other studies as well. Sometimes researchers don't think about anybody but other researchers and try to impress other researchers, but we need to think more about how our research translates to the real world. Otherwise, it's kind of worth nothing, really. And so my hope is at the end of this study we'll have this top 10 list. Like, remember David Letterman's? That's what we need to do for this study. And I think we've already got a couple. During some of the cooking events, we see these extraordinarily high levels of a pollutant called nitrogen dioxide, which we know is harmful to the respiratory system. And we didn't use a vent on the cook stove, on our stove.
Propane, right?
We're using propane to simulate natural gas. So we're not plumbed to natural gas here, so we have a propane tank in the back. But I mean, that's a great example of why you should use your stove hood when you're cooking. And
it's a stove that actually exhausts outdoors, not one that recirculates.
One that actually exhausts outdoors, which this does, right? So, I mean, that's sort of one of those things. Now, that's something that I think a lot of people know, but from my perspective, I don't want to ever see a house built again that doesn't have a stove hood that exhausts to the outside. I'd like to never see a house sold again, even an older home, that isn't going to be retrofitted if it doesn't have an exhaust to the outside. It shouldn't be sold. There should be a retrofit on the house when it's sold.
And I know that Lawrence Berkeley Labs, with their study, found particulate emissions as far as the ultrafine particles, even with electric ranges.
Absolutely. So, the particle emissions from cooking come not just from the natural gas, but they come from the food itself. When you heat up the food, it comes from the frying pan. If you have a Teflon frying pan, it comes from the cooking oils that you're cooking with. Even if you're boiling water, when you boil, you release minerals from the water. They're aerosolized into the air. And so it's not always just the fuel. It's a lot of other things associated with cooking.
I'm going to take the mic for you because I know you're involved.
Okay, thanks.
What's the follow-up question?
So you've been involved here at the University of Texas for how many years?
25 years, quarter of a century, yeah.
And in this time, you've spent a lot of time researching indoor environmental, indoor air quality issues. Is that your primary focus, or has that been one of your primary focuses?
That's been my primary focus for about the last 20 years. So the first 5 years I was here, I was doing outdoor air pollution research and transitioned slowly over about a 5-year period to the indoor environment. And that transition was due to a student who came to me one day and said that she was very interested in doing research on indoor air pollution. And I hadn't given it much thought. And I said, well, that sounds interesting. And we started working together. And the more I read about research on indoor air quality, the more I realized how little had been done, what great opportunities there were to make a difference. And so I transitioned into that field. And it's something, even though the research funding related to understanding indoor air quality and indoor air pollution is far less than research funding available for outdoor air pollution, it's just a field that makes you want to work in it because you're doing good. Any research you do is going to improve the knowledge base, since the knowledge base is, at least then, was relatively small. And because Americans spend so much of their lives indoors, the research we do on indoor environments is so important if it can lead to improvements in the indoor environment, which gets back to your question about practitioners and people on the front lines that can make the indoor environment better. Yeah.
I guess the follow-up question to that is, do you feel that we need to educate both the practitioners and the general public simultaneously? Because like a two-pronged effort. I mean, do you see it more as a push-pull?
I do. I think both. There needs to be education of the general public for sure, and education of practitioners for sure. And some of the public is not going to receive the message, right? They're not going to look in the right places. You can't reach everybody. And so they're going to need practitioners to help them along, those that don't get the message on how to best do things themselves. So I think it is two-pronged. I think it is push-pull.
So how does academia, the research community, how do you, or both academia and private research, how do you get this information, how do you disseminate this out to all of us?
So there's multiple ways for researchers that are so inclined to do it. So I use a lot of social media. I tweet, and I try to tweet in ways that boil down research to, hopefully, things that people can understand. I have, and some of my other colleagues, one of whom is roaming around in the house right now, have gone out of our way to go to IAQA meetings and speak at IAQA meetings, to speak with people like yourself and others whenever we're asked. I would never say no to speaking to somebody who reaches a practitioner crowd, because I'm really, really committed to getting research boiled down to those who can really use it. And I'm not the only one. I mean, there are many in our field, although I think we're probably a minority at this point. We have to have more researchers that think that way.
I know at the Sloan Foundation session that was back in October, I think, that was streamed online. I participated online and watched it. I know Carl Grimes raised a question on the last day of, again, this same topic of, okay, great, the microbiome research is coming down at the end. So what happens next? And, it seemed like the answer was, at least in general, it's like, well, that's not really for us as the researchers to, to do that. And it's like, so that for me online, I was like, well, that's frustrating. What will happen with this information?
No, I think that's a great point. I remember Carl asking a question, I think, too, is to, well, when you're remediating a building, how how much remediation is enough, right? At what point do you say, I've remediated enough that I've gotten rid of enough mold or whatever, and nobody really had an answer for that. So I think the big thing is communication between practitioners and researchers. We ought to be listening to practitioners to find out what questions they need answered, and hopefully they can listen to us to at least learn about what we're doing, and we can boil it down in such a way that they can take it and use it whatever way is best for them. I don't think as a researcher I can tell a practitioner this is how you should use the information, but I should be able to tell a practitioner, here's what we're finding, and this might be useful to you, right? Does that make sense?
No, it makes total sense. I think one of the things is, again, even with the practitioners, I think Corbett mentioned it during the radio show, I think all of us, even forward-thinking practitioners, are befuddled by white papers a little. It's like a big, massive white paper. It's not really good actionable intel for us. So I think it's more important to be able to distill that in such ways that it makes sense to practitioners.
No, I agree. That's why I said at the end of this study, I think there should be a one-page sheet of paper that's a bunch of bullet points that are one-liners that say, here's what we learned that is important to practitioners. You should definitely do this. You shouldn't do that. We've got a whole bunch of low-cost air purifiers we're testing against the most sophisticated air quality weapons in the world surrounding the test house. It's going to be great to be able to compare all these versus those, and we'll be able to boil it down, and hopefully that'll get out to practitioners and the general public so they'll understand what the limitations of those instruments are.
I mean, certainly a $200 test device is not going to compare to a $100,000 test device. But the question is, I guess, does that $200 or $200-ish test device at least give usable information for a consumer level information, trending at least, data logging? I think there's value in long-term trending. And I'm a consultant in the industry too. We go out and we take short-term samples, but at the end of that, we're snapshotting. We're not seeing a trend over building over a month or a year.
No, I agree. I think there are two ways to use those instruments. One is to hope that they give you accurate measurements, but then the other one, which I think is probably the most valuable of these instruments, are they showing us the trends? Are they going in the right direction? If there is a big source of particles in a house all of a sudden, or a big source of all organic compounds, is the instrument actually telling us that, right? So we can do something about the source. And a bit of a trailer and a teaser is that so far most of the instruments are showing the trends pretty well. There are one or two that are not showing the trends very well, right? So those that at least show the trends right should get a happy face, and some of them might be reasonably accurate relative to $250,000 instruments. So, yeah.
So final thought, or final question. So I know you're going to the University of Portland State University, okay, and you're taking on the role of dean.
The dean of the Massey College of Engineering and Computer Science. Yeah.
So that's great. So I guess the follow-up to that is, are you going to continue doing indoor air quality stuff there, or is this a whole different direction for you? Or is this a loaded question?
No, it's not a loaded question at all. So it's a great question. So I suspect my first year as dean, I'm going to have such a steep learning curve and such a tall mountain to climb that I probably won't be doing that much research. But I hope to maintain a laboratory and to do some research over the next decade or so. There's a researcher at Portland State University, a young faculty member who is actually one of my PhD students. His name is Dr. Elliot Gall, and he's got a fantastic, wonderfully instrumented laboratory, and he does indoor chemistry research. He has instruments that are effectively the same as some of the great high-quality instruments you see here in the test house. And so my guess is that he and I will be doing, he'll be doing 90% of the research, and I'll be doing 10% of the research with him.
So can we expect to see you on Twitter still, at the same frequency?
Absolutely still on Twitter. Maybe not the same frequency, but I'll still be tweeting about indoor air quality issues, yes.
Excellent. Well, I wish you the best there. Rich, thank you so much for coming in and joining me today. We're in Austin, Texas at the UTest House for the HOMEChem Open House. I'm Bob Krell from Healthy Indoors Magazine. Thank you.
Thank you, Bob.